Go. So I'm guessing everyone's going to do that survey for extra credit, or?
Yeah.
You guys look like you're struggling. Like you're
Where
paid.
is the weekend? Wait. Hold on.
What happened? You were absent yesterday.
No, I know. Are we still doing 2.3?
Yeah, yeah. We're doing kind of 2.3 and 2.4 mashed together.
Yeah.
Yeah.
So 2.3 I'm assuming we'll do Monday or?
2.3 and 4 is due whenever I finish this whole stream.
Yeah.
So we're going to move on. Did you have?
How are you supposed to know when you hit the server? Just send you the email with a screenshot sign?
Yeah, something like that. Yeah. Where are we? Yeah, so last time we developed what we call the derivative of a function, right? So f of x is a function. Okay, so this was actually a problem on the quiz. How do you define f prime?
Yeah, easy. Limit as h approaches 0 of f of x plus h minus f of x all over h.
Right.
And then the idea is that
And this
once-
is if it exists,
Yeah.
right? It doesn't have to exist. By the way, I also put this in a parenthetical statement, just a vocabulary note. If this exists, the function is called differentiable. F of x is said to be differentiable. At x, right? If it doesn't exist, then it's not differentiable at x, meaning a derivative does not exist. Meaning a function that gives us the slope at that point does not exist. So it stands to reason I'm saying if it exists, and it's called differentiable if it does. Stands to reason there are cases where it doesn't exist. So what's an example? Anyone know an example of where the derivative doesn't exist?
the limit as x approaches 0 of 1 over x.
What? That's a limit, not a function. Give me a function.
1 over x.
Okay, at what point?
As it approaches 0.
Right, 0 is undefined. I mean, okay, let's talk about a function where it's continuous, like on the curve itself. There's no derivative. Can you imagine such a thing?
Yeah, piecewise. It's like that parabola thingy that like it's differential as let's say the limit from both left and right approach a certain point, but when you define at a certain point, suddenly like it's just like somewhere
Okay,
else.
that's still a discontinuous case. Can you think of a continuous case? Very famous example, your textbook spoke about it. No, x squared is differentiable everywhere. The derivative of x squared, we did it last time, is 2x, which it's always 2x. There's no problem with that. Here's an example. Consider the function the absolute value. Note, this is not differentiable. Can you guess the point where it's not differentiable?
0.
At 0, right. That's kind of where absolute value x kind of goes crazy. At 0, it starts to change on itself, right? Right? This guy tends to be a problem, right? And I'm going to show you by the definition why it's a problem. And then I'm going to talk in general about conceptually why this is a problem and how even if you don't know a formula, you can look at a function and tell whether its derivative would exist or not, even if it's continuous there. So yeah, absolute value x is defined at 0. It's a continuous function. You can draw this without lifting your pencil off the page, right? So as far as continuity is concerned, there is no problem. As far as differentiating, finding a function that gives its slope, it does have a problem. Can we see why?
Oh. Wait, no.
We'll say that's your f of x. What is f prime at 0? What would that be? f prime, remember what f prime is? Just write it down here. Limit as h approaches 0 of f of 0 plus h minus f of 0 over h, right? So I just plug in 0 instead of x, right, in this formula. Now what's going to happen here?
So it's literally just gonna be the limit as h approaches.
What is this function?
Just f of h.
It's just f of h, which is?
0.
No.
H.
No. What's f?
The absolute value of x.
Okay, that's f of x. What is f of h?
But there is no f of h.
There is no f.
The absolute value of h.
Okay.
Okay, what's f of 0?
0.
You replace x with whatever is in the brackets. Remember that? We did that.
Oh, you can't cancel the h's.
Right? F of h is just, I go to f of x, everywhere I see an x, I replace it with an h. Boom. F of 0, everywhere I see an x, replace it with a 0. Boom. Okay, so here, obviously absolute value of 0 is just 0. So here I have this limit. Now what's that limit? Does that actually exist?
Wait, now why can't the h's cancel?
You tell me. Why can't the h's cancel? Why can it just be 1?
Because H is not really H's, it's just absolute. It's like,
Okay, what does that mean?
I just know it's not H necessarily.
When it's more than 0,
Whoa.
it does one thing, and when it's below 0, it does another.
Right, it will do two different things. You're approaching 0, but on the left and the right side, you're doing something different, right? Note that if I take the limit as h approaches 0 from the left side of this guy, this is just the limit as h approaches 0 from the left of minus h over h, which gives me minus 1. If I approach 0 from the right side of this guy, absolute value just replaces the absolute value with h itself, which it would cancel, and that would give you 1. Which means this guy does not exist. The limit doesn't exist because left and right don't agree, right?
There was something like that when I first ran, it didn't exist.
Well, it wasn't as simple as that, but yeah, there was an absolute value one. You had to check from both sides. That was the trick. I think there was an x minus 9. Yeah, there was like x minus 9.
It was 3s minus 27.
Yeah, you had to
over
approach
x.
9 from the left and from the right and make sure that it was the same.
Yeah.
Right? Every time you see an absolute value, that's always in the back of your mind. Where is it 0? And you have to approach both sides. Right? No, if I wasn't going to 0, I wouldn't care. I would just either take h or negative h. But because 0 is where things turn over, I have to check it. So it turns out it does not exist. In general, we have the following. This is actually a theorem in your book. So let me actually write it as a theorem. If f of x is differentiable, then it is differentiable at x. Then it is continuous then. So it turns out if you know you can find a derivative, your function is automatically continuous. It doesn't work the other way around though. No. As the above shows, if f is continuous, it does not mean it's differentiable. So you won't always be able to find the derivative. And I'm going to tell you when right now. Boom. F is not differentiable anywhere it is not continuous. So if your function is not continuous at a point, it's not differentiable there either, right? So something like 1 over x, not differentiable at 0. Because the function doesn't even exist at 0. There's nothing to take a slope of. There's nothing to draw a tangent line to, right? Or if you have some kind of function where it's doing something and then there's a jump, not differentiable here. Right? So if there's a gap, a hole, an asymptote, if your function is not there, you can't draw a tangent line to it. So it's definitely not differentiable anywhere it's not continuous, but even more than that, f is not differentiable at any point where it would have a sharp corner. Basically, to be differentiable at a point, when you zoom into that point, the function should start to look more and more like a straight line. If it looks like a sharp corner, this will not work. And if you think about it, graphically, this should sort of make sense, right? So anything that looks like this, or maybe like that, or anything similar. Notice here though, like at this point here, where the sharp corner exists, how many tangent lines can I draw? Tons of them. I can draw lines that touch that thing at one point all over the place, right? So if I say, what's the slope of the tangent line? Whatever, undefined. But the slope of the tangent line is the derivative. Hence the derivative is undefined. And if you take a limit here, if you take the derivative limit, which I erased, it's not going to work, right? So at sharp corners, the tangent line is not unique. The slope of the tangent line is undefined. So if your function is not continuous, or there's a sharp corner, you cannot differentiate there. So derivatives don't always exist, unfortunately. But where they do, they're very useful. They can give us a lot of information about a function. Before we start to talk about some applications, I want to do some more examples. So last time we used the limit definition to find the derivative of x squared. Let's find some derivatives of something else using that same definition, just to get us used to the algebra. Use limits to find the derivative of. We already did x squared, so let's do f of x equals c. C is just representing a constant. B. I'd like to do f of x equals radical x. This was partially done on the quiz, not completely. F of x equals 1 over x. Also want to find the derivative of something a little more, not really complicated. 2 minus x squared minus 1 over x. Find the derivative at x. E. Last example I want to do here is find the equation of the tangent line to f of x equals 3 minus 1 over x at x equals 1. Do 8. What's another word for a derivative?
Prime.
Hmm?
Prime.
The f prime is the notation for it, but what does it mean? What's an interpretation?
The slope of a tangent line.
Slope of a tangent line.
As it
So-
touches something.
If my function is a constant, what do you think the derivative is going to be?
It's the,
1.
What does a constant function look like?
it's just a horizontal line.
It's a horizontal line, right? So this is my function f of x equals c, passing through c. What is the slope of a tangent line to a point here?
Nothing.
Zero, it's a horizontal line. So we expect to get 0 here. So, okay, so if f of x equals c, this means that f prime of x would be equal to, what is it? How do I find derivative?
X plus E.
No,
Limit
limit.
as x approaches to 0 for h of f of x plus h minus f of x all over h.
Okay, so here, what's f of x plus h if this is our function?
C plus H.
No. Getting back to basics, what does this mean?
This shifted over like H units left.
No. If I know f of x, what is f of x plus h? How do I compute it? What do I do? F of blah, f of something, what do I do?
Blah plus A.
If I see f of 1, what do I do?
1 point x.
Plug 1 into x, right? If I see f of 3, what do I do?
1 3
If I see f of smiley face, what do I do?
Why was it squared plus 1?
F of x plus h, what do I do?
Plug X plus H everywhere you see X.
Exactly, where do I see x?
Nowhere.
It's just itself. Where do I see x? Nowhere. This means wherever I see x, I replace it with this. There is no x, it's itself. Okay? C minus c is already 0, there's nothing to do here. Derivative of any constant is 0. Remember that. Doesn't matter how crazy the concept looks. So if on an exam I give you something like this, find the derivative. Oh my god! It's a constant, it's 0. It's a trick question. If you try to do anything else, okay. Derivative of a constant is always 0. I'll state that fact formally in the next section, but for now you can know that's true. Okay, let's do something. Let's actually do something. What about radical x? What's my derivative?
Are you sure you put x 1/2 first?
X 1/2 where?
No, sure you can do that first, change it to x 1/2.
I don't particularly think it's going to help. How do I find the derivative?
Limit of h as it approaches 0. F of x plus h minus f of x all over h.
Until you can say that in your sleep, write it down every time you're finding a derivative using limits. Okay, so this is going to be limit as h approaches 0 of, what is f of x plus h? Square root of?
X plus h.
Like that. This is inside, right? The x is replaced by x plus h. Minus f of x is parentheses. So whatever, it's just one term. So we have that. How do I simplify that? I'd like to plug in h equals 0, but I can't. What do I do?
Oh, you factorize it.
How am I going to factor?
You multiply both the top and the bottom by x plus h radical minus this thing.
The conjugate.
Plus.
The conjugate, right? This is called rationalizing, not factoring.
Oh, sorry.
Right? So you do that. What does the top become?
S.
X plus h minus x, right? Because it's the difference of two squares forms. It's going to
Or
be this
just
squared
h
minus
at that
that
point.
squared.
Or just h since
It's
the
going to be
x
just h
cancels.
at that point. We're going to have x plus h plus radical x here. This will die, the h's will cancel. I end up with the limit as h approaches 0 of 1 over radical x plus h plus radical x. At this point, I can plug in h equals 0, and I would get 1 over 2 radical x's. So that's actually a formula that gives you the derivative. Notice that the derivative does not exist at 0, right? Because in the square root function, it starts like this and goes like here. At this point, you can draw all sorts of tangent lines here, right? It's not well defined there, it's not defined. But at any other point, there's literally only one line that's tangent to that curve. 1 over x f prime equals
Limit as h approaches 0, f of x plus h minus f of h all over h.
x over h. What's this? 1 over x plus h minus 1 over x all over h. How do I fix that?
You could multiply by the common
The
denominator.
LCD?
Yeah.
So I can multiply by x times x plus h, do that on the top and the bottom so we're not changing the value. Multiply out, the x plus h's would cancel here, I'd just be left with x. Multiply out here, the x's will cancel here, parenthesis, I'm left with x plus h over h times x plus h. X will kill x, negative sign would distribute, and I will get a minus h on the top. H's cancel, and at this point I can plug in h equals 0. So I get minus 1 over x times x.
X squared.
Minus 1 over x squared. What was our other function? 2 minus x squared minus 1 over x. Prime of x equals?
Limit as h equals to 0.
f of x plus h minus f of x all over h. It's gonna be the only thing.
It's gonna be the only thing you know how to say.
It doesn't exist.
That's how you should feel. You should say it so often until you're so bored saying it. It's like, yes, yes, I know already. Okay, so what happens here? What does f of x plus h look like?
Well, 2
2
minus
x squared.
0.
2 minus what?
X
H
squared.
X plus h squared,
1 over x plus h.
1 over x plus h, minus.
Oh, minus
The whole thing.
that whole function in parentheses.
This whole function in parentheses.
Over h.
Okay, what do we do here? Well, the 2 will kill this 2 right away, so that's nice. What else is going to happen?
The x squared.
Well, you gotta
That's
expand
fact- yeah.
the x plus h squared.
And there's a negative sign in front of it, so it's actually going to be minus x squared minus 2xh minus h squared
1 over x plus h. minus
plus x squared plus 1 over x.
x.
Now x squares will kill each other. Now what? Couple ways you can deal with here. You could do this exactly the same thing. Multiply top and bottom by the LCD. Brute force it. But it's kind of a waste on these guys, right? You really need to do that for the fraction. So you could actually split this guy in 2 because we have that limit rule. The limit of a sum is the sum of the limits, right? So I can actually think of these as 2 separate things. I can only do my mumbo jumbo over here. We already did that actually, so I'm not going to redo it. At this point, I can factor out an h and cancel. This h is going to kill that and one of those. So this ends up being the limit as h approaches 0 of
2x
minus 2x minus h. And this guy is actually going to, it's the negative of that guy, so it's just going to give me, instead of a minus, it's going to be a plus 1 over x times x plus h. And so now, we take the limit of all of that. We get minus 2x plus 1 over x squared. Which one was that? The A, B, C, T. This was D. So yeah, problem like this guaranteed to come on the second test. I'm going to give you a function and say use limits or use the definition of derivative to compute the derivative, and you have to do all this algebra. A problem like this is also going to come up on the second test for sure. You have to compute the tangent line to something. Okay, how do I do that? Right, I need to first find the derivative. How do I find the derivative?
Right?
Limit.
Limit of
So this is going to be the limit as h approaches 0. This guy, plug in x plus h instead of x, minus, open parenthesis, copy the same function down, over h. The 3 minus 3 is gone. This is minus 1 over x plus h, plus 1 over x, all over h. We actually dealt with this guy before, so dot, dot, dot. We get minus 1 over x squared. Okay, so we get to that. Now what?
Plug in 1,
Plug in 1.
wherever x is.
This means that f prime of 1 is
Negative 1 over 1 squared.
negative 1 over 1 squared, which is minus 1. What's that minus 1?
The slope.
Slope of our tangent line. That's going to be the n, right? So now what?
plug it into a linear.
Right, tangent lines are linear. So now I have the slope. Is that all I need for a linear equation?
You need the y-intercept.
Okay, how do I get to that?
Plug in 1 in the original equation.
Plug into what equation?
The original one of x.
Why would I do that?
To find y from.
Alright, so I know if x equals 1, then my y is just going to be f of 1, which I would plug into this equation. 3 minus 1 over 1, which is 2. So this means 1 comma 2 is on the line.
And then you do like y minus
Y1.
2.
Y minus y1 equals mx minus x1. We encourage you to write down a formula every time you're doing something, which means, yeah, y minus 2 is equal to
Equals to negative 1 times x minus 1.
that's your tangent line.
And,
Oh, you can leave it like that?
Yeah, sure. At the end of the day, you kind of follow instructions. I didn't ask you to simplify or write it in a certain form, so whatever. Yeah, so that's how you find a tangent line. The derivative gives you the slope of the tangent line at any point. So if I want to find a tangent line at a certain point, I find a derivative, plug in that point, and then Once I have a coordinate and that slope, I can find the equation of the line. Very common problem. We don't go deeply into this at this point. We will come back and do some very important applications. But I just want to mention some things I think right now. So how you can start to think about derivatives in many contexts. A couple of kinds of interpretations. One, there are some directly related to something like physics. Calculus is all over physics, particularly something like motion, right? Common notation is S stands for position. I don't know why S stands for position. That's a very common variable to use for position. So if you have a function that gives your position at any time t, right? When I plug in t, the output of S tells me my location, right? Then it turns out that if I take S prime of t, what does that give me?
Velocity.
That would give you velocity. Right? I kind of illustrated this with a graph before when we did that distance versus time thing. And the slope actually gave us the speed, right? It gave us the distance per unit time, right? So this is position, which you can think of as a distance function. And the rate of change of distance with respect to time, well, that's velocity. If I take a derivative again, right, which I'm going to talk about that presently,
That's
or the first
acceleration.
derivative of velocity, this gives you acceleration, the rate of change of velocity. Right, so derivatives can help us figure out, if we know where something is, I can tell you how fast it's going and how fast its speed is changing using derivatives. There are things like, of course, business, money. Things like if C is a cost function, or R is a revenue function or something similar. Revenue function. Then, if you look at C prime of X, this is called the, does anyone know? There's actually a marginal. There's a technical term for it, it's called the marginal cost. Right? And which is, how would you describe the marginal cost? Right? Usually X would be the number of products, right? So it's the number of products you sell or manufacture or something, and you have a cost based on how many things you're producing, right? So in this case, what would the marginal cost mean? How would you interpret it?
How much more would all the products cost for every extra unit? Something like that.
Almost. We need to work a little harder to get that, just a little harder. But at this point, it just tells you. But yeah, you can use it to approximate how much you expect it to cost to create one more unit. You could use it that way. So if I have a cost function and I find the derivative at a certain point and it gives me 10, then on average to produce one more product, it will cost me $10 more. Right? You can think of it that way. It's how much the cost is increasing. Similar for revenue. It's also called marginal. So usually when you're dealing with finances and you're talking about derivatives, marginal is the word that they use. Because you're at the margin, you're at the edge. So this is marginal revenue. And so it's the rate of change of revenue. Right? So it's how fast your revenue is increasing at the X product.
What would the second derivative of all those marginal cost revenues be?
Well, I'm going to talk about second derivatives soon, so after I do that, we can talk more about that. Revenue, rate of change of revenue of the at so that's one other application. Of course, there are almost anything. Anything that's changing where you can measure a speed of how it's changing, you can apply a derivative to. It's that versatile. So, but these are the main ones mentioned in this section. Things like population. Now remember, these are usually described by exponential functions. We'll talk about derivatives of exponentials soon. But yeah, so if P of t is a population function, and P prime is the rate of growth of the population. So it tells you how fast people are being added to the population proportionally. And so I think in this section, it's more like they tell you a word problem, but you never really do anything. They just ask you, interpret what the derivative would mean in this case. Right? Derivative is always sort of talking about a rate of change, how something is changing. How fast is it increasing, how fast is it decreasing, or something similar. I just want to have that stuck in your minds for a second. Once we learn a few more advanced techniques about derivatives, we'll go back to word problems and applications, and we'll talk and we'll look in depth on how they affect things. So those are some of the main applications they spoke about here. I already talked about differentiability and continuity. Let's talk about the second derivative. As the name suggests, this is the derivative of the derivative. You take a derivative and then you take it again. Right? Remember, the derivative is a slope, so this measures how fast the slope itself is changing. So you're measuring how the rate of change is changing. Now, once we start looking at that, let's start examining how slopes might behave for different kinds of functions. So let's say I have a function that's doing that. Versus a function that's just increasing in a straight line. Versus I have a function that's doing this. Okay. So let's talk about, now we're not looking at the function itself. I'm kind of looking at the slope of the function, right? So let's try to find some tangent lines here, right? Here's one tangent line. Move over here. Here's another tangent line. Move over here. Here's another tangent line. What do you notice is happening to the tangent lines here?
The slope's decreasing.
The slopes are decreasing. Here it's super steep, very positive. Still positive, but it's less positive. It's less steep. Still positive, but less positive, right? The slope's actually decreasing, right? Notice that here, I'm calling all these that. Here, f is increasing, but at a decreasing rate. Right? So it's increasing, but it's increasing slower, right? So you're always adding to the function, but the amount that you add at every step is getting smaller and smaller and smaller, right? One way you can see this as well is that the tangent lines are always above the function in this region, right? So keep a note of that, call this case 1. Let's look at case 2. What do I know about the tangent line here? It's pretty much the function itself. Slope is constant. Which means not changing. This means function increasing, but at a constant rate. Right, which means you're increasing, but the amount you're adding per unit time is always going to be the same, right? So you're moving linearly. Right?
So would there be a second derivative?
Oh, in this case, the second derivative would be 0. Right? So we're actually going to get to that later. Here, start to draw tangent lines. Look at what's happening. The opposite. We're increasing, but we keep getting steeper. We're increasing by more and more. Right here, f is increasing at an increasing rate. Notice that tangent lines are always below. Right, so just to give you an idea of what's kind of going on, log functions would behave sort of like this. They can always be increasing, but they're increasing by a smaller amount each time. Exponential functions would increase like this. They're always increasing, but they keep increasing by a larger amount every time, right? Linear functions, they're always increasing by the same amount. It's kind of why eventually, even if in the beginning any of these guys can win, eventually when you get to infinity, this guy's always going to beat all the other guys, right? Because as time goes on, you keep adding more to him than the other guys. There are words we can use to describe this kind of behavior. We're not going to care too much about applications at this point. How about case 1? A function that behaves like this, meaning our tangent lines are always above the function. We're increasing, or it could work out as decreasing as well. But the tangent lines are always above the function on an interval is called concave down on that interval. Right? So it could look like this. It could be increasing and concave down. It could also be decreasing and concave down. Right? But in general, the shape is kind of like this. That's called a concave down function. Right? Notice that you could be increasing and concave down, or you could be decreasing and concave down. Doesn't matter. Right? This is just concave down, both increasing and decreasing. Right? How do you want to remember it? Concave down like a frown. You're down. You shouldn't step. You should like this. Concave down. So concave down, down like a frown. It's actually, geometrically what it means is that our graph is shaped like a frowny face, right? If we're not worrying about applications or interpretation here, the geometric is how the graph is shaped is called its concavity. Case 3, this last case that I just dealt with. You guessed it, concave up. Again, I want to emphasize, it has nothing to do with increasing or decreasing. You can be increasing concave up. You can be decreasing concave up. Or it can just be concave up in general, where you're both increasing and decreasing at different points. Right? How do you remember this? Concave up, like a cup. Up like a cup. Also, you're up, you're feeling happy. You smile. You're feeling up, you're concave up. It's talking about the shape of this graph. So concave down, tangent lines are always above the function. It turns out that graphically this makes the function shaped like a frowny face. If your tangent lines are always below the function, graphically it makes your function shaped like a smiley face, right? This smiley face is called concave up like a cup. The frowny face is called concave down like a frown. So the interpretations here graphically, well, we're pretty much done here. So we're not completely done with this section, so no homework. But yeah, graphically, concave up talks about the shape. The second derivative would tell you about this kind of thing, and now I'll explain exactly how next time. And the first derivative sort of tells you about increasing, decreasing. So if you want to figure out about increasing, decreasing, use the first derivative. If you want to figure out about the shape of a graph, use the second derivative. And there will be other interpretations to use, but we'll pick up with those next time. And we'll finish 2.3 and 2.4 on Monday. I'm thinking the test I'll want to move to Tuesday at least, because I'll post some review problems this week, and I guess Monday I want you guys to be able to ask me about them. So I'll make the test on Tuesday instead of Monday. For now, so spend the weekend. I'm going to put up the answers to that quiz I gave today, so you can spend the weekend going over that stuff, make sure you're solid, and going over the review problems. I'll see you guys on Monday.
Have a good weekend.
Yeah.